So welcome everybody. We are definitely excited to have our, RF webinars in series and offering you this great information. We see a lot more trends in RF, complex RFs, as well as simple RF. But yeah, it's definitely a growing market for sure, at least for Sierra. And if for any of you who don't know who Sierra is, Sierra Circuits is a PCB manufacturing company and a assembly company, and we also do component management or for our customers. And we've been manufacturing in the Bay Area, um, and with about 100,000 square feet of manufacturing, and we specialize in a little bit more complicated boards, and we see the trend is getting more and more complex for us. And then we want to be able to provide more information to designers, not just manufacturing guidelines and capability guidelines, but also information like this. Our vision is that if the customers succeed, then we succeed with them. So this is the agenda for today. It's kind of a lot of details, so we'll try and get through them quickly so you can ask your questions and go on with your day. So let's start with some high level, common mistakes RF engineers or basically any engineers getting into RF can make during, their layout phase. Definitely RF is a journey, and there's definitely lots of prototyping that happens. So try and take what you can from this webinar and presentation and our design guides and see, help you hopefully improve your journey. So, you want to make sure that, of course, you match impedance across the RF components. If you don't, you can get reflections and signal loss. So, the other kind of issue is just when you route your RF signal paths, avoid the sharp bends, unnecessary vias that I could say are in the way. Inconsistent, trace widths can all lead to signal distortions. Via design is a key thing. Using strategies like laser drill vias or back drilling can help reduce any long stubs. And then component placement is key. So you don't want to make the mistake of placing components without considering your return paths and current flow. And then don't make the mistake of creating unintended ground loops and split ground planes, and of course, introduce noise and cause unpredicted circuit behavior. So impedance mismatches are often caused by poor layout decisions. So if you look at a few factors that can introduce discontinuities in the signal path, using incorrect trace widths without considering target impedance values, abrupt trace width changes during routing, ignoring copper thicknesses and dielectric heights in impedance calculations. That's an easy consideration. Um, Knowing what your solder mask thickness is post manufacturing, I think is a nice little nugget. So if you get a cross section of your board after manufacturing, you can understand your model a little bit better. What was the thickest of the solder mask and the copper weights and the dielectric press out thicknesses, and you can feed that back into, your own models and information, leading to continuous improvement. I think that's a key point here, not necessarily mentioned. And so, yeah, so these are some of the key things. And then impedance discontinuities can often arise at specific locations. So take a look at these areas, carefully. So the interface between a trace and a component pad, transition between a trace and a via, trace and connector pin interfaces, junction between an RF component and an antenna feed line. So these are some of the key areas to look at on your layout. And to ensure consistent impedance and minimizing your reflections, here are some techniques that you can follow. So do your best to maintain uniform trace width throughout the RF signal path. Um, I was just at KeyCon, and there are some very powerful constraints you can put into KeyCAD, as well as Altium and Cadence, and uh, you know, to kind of take what you can from this learnings and then try and put those into your constraints. I think that would be a great thing. Keep your trace lengths, short between component pads and the connecting signal lines. Avoid necking down traces excessively. Taper traces to match the connector pin width, an SMA pin, for example, to 50 ohm microstrip lines. Add LC matching networks for impedance tuning. At the antenna feed, use quarter wave transformers for impedance transformation between stages. Expose your solder mask over critical RF traces to maintain consistent dielectric behavior. That could be a good solution as well. And I think we're going to do a demo.
So this is Sierra Circuit's impedance calculator tool. It uses the 2D numerical solution of Maxwell's equations for PCB transmission lines and renders fairly accurate results. Our impedance calculator tool supports 82 impedance models. As you can see, we have multiple geometries here, like the coated microstrip, uncoated microstrip, embedded microstrip, and the strip line. And for each of these models, you can choose the single-ended differential pair or the coplanar models here. The tool also integrates with the signal loss, crosstalk, and the S parameter calculator. I've opened the coated microstrip differential pair impedance calculator here. We'll start by entering the input dielectric information. Let's enter 3.348 for the dielectric height H1, a dielectric constant ER1 of 3.63, a coating height of 1.5 mils. We have the coating height H2C and coating dielectric constant ER2 with a default value here, but you can change them if you wish to do so. And enter the coating height H3C here. Then we have delta W here. Delta W is nothing but the difference between the top of the trace and the bottom of the trace. You can click on this help content here and it displays a table that suggests delta W values based on the starting copper weight. You can use this as a reference. Let's go with 0.5 for now. Enter the trace thickness, a trace separation, and to calculate the trace width, we enter the target differential impedance and click on calculate W. You can also do reverse calculations here wherein I enter the trace width and we can calculate the differential impedance instead. For example, I'll just change this into 5 mils and click on calculate ZD, and the differential impedance and the other parameters here are calculated and displayed. Then we have the signal loss calculator in the other tab for the same chosen model. All we have to do is enter the dissipation factor, the frequency, surface roughness. 6 is the standard roughness for a foil. Let's go with a length of 2 inch. Click on calculate loss and the signal loss output in the odd and even mode are calculated and displayed. Similarly, we have the S parameter calculator. Just enter the source and the load impedance. Use this drop down here to select the output type and click on calculate S parameters. Here the characteristic impedance, the propagation constant and the 4-port and mixed mode S parameter results are calculated and displayed. One thing you have to make sure before using the S parameter calculator is that you need to use a signal loss calculator before, because the frequency that we have entered there is used for calculations here. So you can always go back to the signal loss calculator and change your frequencies to calculate S parameter at different frequencies. Then we have the crosstalk calculator. Enter the coupled trace length, the signal rise time, signal voltage, and click on calculate crosstalk. And the near end and the far end crosstalk results are calculated and displayed. Thank you so much.
Okay, so hopefully we have some good images for you and to help you with your layouts along with the bullet points here. And again, if you have any questions or any recommendations, if you are yourself an RF expert and think we missed something important, please absolutely contribute. I really like to see the discussions in the webinars and also in our discussion forums. It's really nice. So, one thing that you have to consider when you're routing your critical signals is try and you know avoid the long trace lengths or stubs that would unintentionally act as antennas. And then, of course, incorrect termination resistor placement can lead to signal ringing and reflections. Inconsistent spacing in differential pairs can affect the signal integrity. Although I think that a lot of the tools out there kind of handle that now, um, you know, very well, as long as you use them. And then unequal length or shape can cause phase and delay mismatch. You don't want to route noisy signals near the RF traces where you can induce crosstalk. Although test pads are fantastic, be careful where you place them. And then, you want to avoid large loop areas and signal or ground paths, which might increase your EMI. So 7 essential trace routing rules to preserve signal quality in your layouts and your RF layouts. So keep your trace lengths as short as possible to avoid the signal attenuation. And incorporate series or parallel termination techniques to avoid reflections. For a series termination, a series resistor is placed between the driver and the transmission line in series to match the line impedance, whereas in parallel termination, a shunt termination resistor is placed in parallel with the receiver to prevent, the ringing. Keep the number of bends and vias identical for both lines of differential pairs. You want to isolate your RF traces from non-RF traces to avoid coupling. And for coplanar waveguides, maintain a uniform gap between the RF trace and the adjacent ground pores. Avoid placing test points on the RF lines since they might cause impedance discontinuities and increase your parasitic effects. And you can remove your solder mask. You don't need your solder mask, so you can remove the solder mask from an RF track. And if you do that, have a good gap between so that the registration is not an issue for your manufacturer, the registration of the solder mask to the imaged and etched trace. Okay, via design. Vias can introduce, and when not designed properly, unwanted impedance changes and signal degradation. So avoid unterminated via stubs. Uh, Avoid using too many vias because you might actually increase your parasitic inductance and capacitance. Avoid lack of adjacent ground vias can disrupt return path continuity. As asymmetrical vias usage in differential pairs can lead to skews, and oversized vias and antipaths create impedance discontinuities. You want to place your vias as close as possible to minimize the inductance. Place vias evenly along both sides of the transmission line to isolate noise from the nearby traces or ground layers. Do not place power signal vias adjacent to each other, have ground vias between them to reduce loop areas. Always match via impedance with the connecting RF line impedance. And here's a little snippet from one of our podcasts.
A lot of the designers I know believe that making vias larger drastically reduces inductance. Now, in truth, it does lower inductance. Two vias in a 62 mil thick board, 1.6 millimeter thick board, that are 10 mil drill and a 20 mil pad that are a quarter inch apart will have an approximate inductance all the way through the board of about 2.5 nanohenries. If you make the vias twice that size and leave them a quarter inch apart, the inductance will drop down to about 2 nanohenries, which is a reduction of about 20%. But that's all it is. If you take those two small vias, instead of leaving them at a quarter inch, put them where they're close enough together that the pads are separated by 8, 10, 12 mils, the inductance of those two small vias will drop all the way down to a nanohenry. So they go down, yeah, it's a huge, it comes back to what we said a little while ago. Inductance is a proximity effect more than a size effect. And that's why people think, oh, lots of vias, really, and that's another mistake people make. They'll put power via, power via, power via, power via all next to each other, thinking that that lowers inductance. All that does is drive inductance up, and I don't have time to explain why because it's really deep, but it's called the solenoid effect.
Right.
You need to do power, ground, power, ground, power, ground. You need things in pairs, and you need to exchange power next to ground, next to power, next to ground.
Loop area
You're
reduction.
creating small loop areas. Thank you. Well said. It's exactly what
That
it
is what it's required.
It's all about loop area.
Download our signal integrity design guide to learn more.
So we are talking about via impedance calculator here, which uses the physical dimensions of a via to calculate its capacitance, inductance, and impedance. The tool implements numerical solutions of Maxwell's equations again to render accurate and consistent results. Our tool supports two types of via models. As you can see, we have the through-hole via and the laser via. Each of these models has 4 via structures. The through-hole via with single and 2 reference planes, and the through-hole backdrill via with single and 2 reference planes. Similarly, in the laser via, we have the blind and buried via with single reference plane and 2 reference planes. So let's just demo the through-hole via with a single reference plane for now and enter the dielectric information. Let's enter a height of 29.5 mils for H1. The dielectric constant below, for the dielectric below the reference plane, we'll enter 4. For the height of dielectric H2, we enter 29.5 again. For the dielectric constant of the dielectric above the reference plane, let's go with 3.6. And then we have the dielectric constant of the dielectric in the inner surface of via. Let's just go with 1 here. Then we enter the via information. Let's go with a via diameter of 6 mils, an antipad diameter of 24 mils, annular pad diameter of 16 mils, the via pad diameter of 7 mils, the via plating diameter 1 mil, then annular pad diameter of 1.5 mils, and a reference plane thickness of 0.7 mils. All we have to do now is click on calculate, and the outputs, that is the capacitance, inductance, characteristic impedance, the propagation delay per unit length, and the effective dielectric constants are calculated and displayed. You can always go and check out the help content here to explain the term that we have used here or the parameter that we have used here. Thank you.
Okay. So incorrect placement of RF components might also cause interference, detuning, signal loss. So watch out for some of these common errors. Placing sensitive RF components near noisy digital or power circuits, failing to minimize RF signal path lengths, mounting components or metal objects like screws too close to antennas, locating matching networks far from the antenna or RF component, placing RF components near the board edges, routing or aligning multiple RF components too close or in parallel. So you want some strategies to place the components in ARP designs. So position your antennas at the board corners to minimize interference from other elements. Arrange components in a linear signal path to reduce trace lengths. Minimize trace lengths between components to reduce parasitic inductance and capacitance. Keep switching regulators, microcontrollers, and other noisy digital parts away from the sensitive RF paths. And then place decoupling capacitors as close as possible to the power pins of RFICs. If you're placing an antenna on the top layer of the PCB, ensure the heatsink is on the bottom layer and vice versa to avoid unwanted coupling. You definitely don't want to create unintended loops or split ground planes. So, definitely these are some of the mistakes that, might disrupt your return current paths. So routing RF signals over gaps or slots in the ground plane, inadequate ground vias between the layers, creating high impedance return paths, isolated ground paths or polygons not tied to ground planes, intentional or accidental splits beneath the RF signals, not connecting hands, shields, or metal enclosures to the ground planes, using thin traces instead of solid copper pores for grounding, sharing the RF ground with noisy circuits like switching power supplies or microcontrollers. You want to also avoid splits or slots in the ground planes, ensure a solid ground plane under ICs to carry return currents, and fill the space between the shield cavities and RF circuits with a ground pore. Use a solid ground fill pattern rather than a hatched pattern for better shielding and lower impedance. Make sure the ground pore is connected to a ground plane. A floating ground pore might act like an antenna. Implement via stitching to provide multiple low impedance return paths. And then we have our spacing guidelines as always. One thing about hatched patterns, so we probably have in our design guide, use hatch patterns for, flex boards. But the truth is you know, if you're only bending the flex once to install, maybe a hatch pattern is not needed. And so you'll get better performance if you don't hatch or don't use hatch patterns. So consider your application carefully for your rigid flex. And then for optimal via-to-via spacing, should be determined through calculations, aka use our calculators, and tailored to the specific design requirements. And so this table will show the maximum spacing between stitching vias corresponding to the different frequencies. Should be helpful. I get a lot of questions about from a manufacturing standpoint, if we have different, via sizes, does that increase cost? Not anymore. Most drill machines are already, have all the canisters of drill sizes, and the machine just swaps out whatever drill size is needed. It used to be that, setting up the tooling for your job, if there's, n number of different drill sizes, could be a little bit more time consuming and labor intensive, but that doesn't really exist anymore today. So don't worry about that. You should optimize your design and not worry about that, especially, when you're trying to get your RF design to work. One point that, these are the regulatory standards. I think it's a good slide, and our other experts can speak better to this. One thing which I want to, really hone in on, it came up recently with one of our good customers. They have a very critical RF board, and they actually didn't call out all the tolerances that were critical to their design. So on iteration number 2 or 3 of that prototype and small production, they're noticing variations in their performance, and lo and behold, that critical feature wasn't really called out on the drawing, and it didn't really give us a clear signal as to, what is acceptable and what is not. And this is beyond the IPC, guidelines. It's really to their application and their performance that they're looking for. So my ask, the learning that I had this week that I want to share is that the more kind of guidelines you can put on your drawings of what you're expecting. That will set up your fabricator for success from the get-go. So know what's important to you, and then make sure that note is on the drawing and that detail is there, so that you're starting from the beginning of your iterations of prototypes with that expectation.